Yeah, it counts down. It's pretty, I mean, this is no low-class budget stuff we got going on here. This is Rankin Technical College, and what we try to provide is the all-around educational experience that you don't get at normal colleges.
That's bullshit.
Yeah, pretty much. So, today's objectives, should you choose to accept them, are to define the AC motor drive subsections. What are the subsections of an AC motor drive? I've told you this 2 days in a row now. You should have it down pat. No.
Stator and rotor.
No. Converter,
Oh yeah.
filter, inverter. The converter takes the AC three-phase or single-phase, doesn't matter which, and converts it into DC. The DC filter then filters it and turns it into viable, pure DC. And then through the filter, it runs through a series of transistors called IGBTs that invert it back to what we call PWM, or it converts it back to, let's call it synthetic sine wave or synthetic AC. So we're going to take the purpose and operation of an AC motor drive subsection. So we just did that. We're going to identify the symbol used for an IGBT or a bipolar transistor, bipolar gate, insulated gate bipolar transistor. That's what IGBT stands for. We're going to describe how the PWM principle of an AC drive. The PWM principle is pretty simple, right? Those IGBTs are switches. They turn on and off. They're dealing carbs, right? They're throttling it to try to keep it at a specific magnitude and a specific frequency. Then we're going to describe how PWM produces an alternating current. I just did that. And we're going to describe the volts over Hertz principle. I did that a tiny bit yesterday. I introduced that, talking about the volts over Hertz principle, right? If we start messing with the frequency, we start messing with the reactance that's going on inside that motor. We start messing with the CEMF, the counter electromotive force, that resistance that's in that motor from the magnetic field. Okay? We start messing with that. When we mess with the frequency, we mess with that, which can raise or lower the amount of current that the motor draws. One of you yesterday, which one was it? We wound it up to about 100 hertz, 90 hertz, and you saw that the current drop went down to almost nothing, right? Because raising that frequency up above the rated actually killed the resistance in it. So, describe the volts over Hertz principle. That's what we just did, and we're going to state the importance of volts over Hertz ratio in a three-phase motor. And the importance is you can overcurrent the motor. What'll end up happening is at lower frequencies, you're dropping that resistance to a point where you're going to start getting nuisance tripping on your drive. It's going to say overcurrent on the drive, or overcurrent, overcurrent, overcurrent. I'm not overcurrenting this drive. But if you don't have the volts over Hertz ratio, it would cause that. Okay? So like, if you're not running the drive in volts over Hertz, if you're running it, say, in vector mode, where you just turn it on and run it at a specific speed, no matter what the load is, you could have this higher current on it and start giving nuisance tripping. So, that's what we're going to talk about. You should be able to do these labs. Have any of you done these labs? 42, 43, 44?
44.
Yeah.
Yep.
So, good deal. We're about on schedule. This picture, you've seen this picture before on one of the other slides. AFDs, adjustable frequency drive, variable frequency drive, VFD, AC speed drive, or ASD, variable voltage inverter, or just current source inverter, or pulse width modulated AC drive. Some people just call them inverters. You can shorten it, just call it an inverter. Your inverter isn't working, right? Or your drive isn't working. Some people just call them a drive. All right. Variable frequency drive seems to be the buzzword now. Most guys are calling them variable frequency drives. Some older guys, you'll hear them called speed drives. Okay, your speed drive's jacked. You got to go fix it. Okay, or I've heard people call them inverters, or I've heard people call them speed drives. I've heard people call them variable frequency drives, VFDs. Okay, VFD seems to be the term that most people are using nowadays. Doesn't matter what you call it, they're all the same. Okay, they all do essentially the same thing to a motor. They all operate basically the same, and they are troubleshooted. Is that a word? Troubleshooted the same way. Troubleshotted.
Dear Lord.
What? What's the matter, Randy? You taking notes? Troubleshooted. All right, so as promised. discuss the block diagram of an AC motor drive, a VFD, speed drive, whatever you want to call it. So the first part of it is called what? You guys remember?
Converter.
The converter. The converter. That will be on a test, almost guaranteed. The converter takes that AC sine wave, whatever the input voltage is. It doesn't matter, if, like I said, if it's single phase or three phase. We have PowerFlex 40s in the side room over there, training tools that run off of 120 volts AC. Okay, 120 volt input, three phase output, 230 volt three phase output with 120 volt input. All right, it doesn't matter what you put into them, you can get three phase out of it. That's why they work, or that's why we use them. So the first part's called the converter. That is correct. It's made up of a series of diodes, forms of rectifier, bridge rectifier. The next part's called what? A capacitor or a filter, right? Sometimes you'll see a little inductor right here in series with the capacitor that is called a choke filter. Some of them have, some of them don't. It just helps smooth it out a little bit better. A capacitor's main goal in life, or its main mission in life, is to do what? Anybody remember?
Capacitate.
Capacitate. Good job, Randy.
Smooth out the DC.
No, a capacitor's main goal in life is to resist changes in voltage. That's its goal in life. Anytime the voltage tries to change, voltage being pressure, right? All those electrons grouped up to form pressure or force, the capacitor will release whatever electrons it has stored. That's how it works. Which keeps the voltage the same. That's its goal in life, is to resist changes in voltage. An inductor, or a choke, its main goal in life is to resist changes in current. All right? So both of them put together smooth out the current and the voltage. That's why we put choke filters in things too. You guys got all that? So what's the last part here? Made up of these little guys down here. The inverter. The inverter is formed by having a bunch of transistors. In this case, they're called IGBTs. The inverter takes that DC voltage, that bus voltage, and it puts it through a series of switches, quote-unquote switches, and it produces a synthetic sine wave, a synthetic AC. All right, let's call it synthetic AC, just to make it easier to understand. Does anybody not understand this principle? No? Yes? Maybe? Is anybody still conscious?
Barely.
Say nothing if you're not conscious. Pulse width modulation is the voltage control method. The AC drive converts AC line power to fixed variable DC voltage. The output section of the PWM AC drive controls both the motor voltage and the current, controlling the area under the group of pulses. It also controls the frequency. The motor is provided the same voltage force at different frequencies. The PWM. What's PWM stand for? Anybody remember? Pulse width modulation. Outstanding. In this type of drive, the diode bridge rectifies it, turns it into DC. The DC is then filtered. The DC filtered voltage is then put through a series of IGBTs that turn off and on as fast as humanly possible to generate the proper RMS voltage levels. These IGBTs are turning on and off like 300,000 times a second, 200,000 times a second, right? 200K, 100K. Most of the switching frequency, they call it, is usually about 16, 15K, but they can turn on and off as many as 500,000 times a second, 500K switching frequency. Okay?
So I would imagine it's really hot.
They get really hot. That's why they usually have fans, and that's why these inverters put out a lot of heat. They really do. Bless you. So how does that work? How does that PWM work? Does anybody know? Does anybody know what this thing's called?
Doesn't it pulse really fast?
It pulses really fast. Good job, Randy. It pulses really fast. But how does it pulse really fast? And how does it create a sine wave without knowing what the sine wave is supposed to look like?
Electricity.
Electricity. Good job. Does anybody know what this thing's called?
It's
A triangle. Good job.
It's one of the gates. It's an AND gate.
It's not a gate. It's not a gate. It's like a gate. It performs eerily similar to a gate. It's called an op amp. It's an amplifier, right? It's an amplifier. And what it does is it takes this triangular generated signal. This signal comes from the processor, from the computer. Okay? It's called the sawtooth. That sawtooth is fed into that op amp, along with this generated signal of this AC sine wave that it wants it to mimic. Okay? So, it takes both of these signals and then it creates pulses. Every time both of them kind of interact, they cross each other, we get a signal out. That gives us our pulse. Blip, blip. Okay? So, it kind of looks like this. You have your AC sine wave over here just kind of doing its thing. And then you have this sawtooth that's being generated by the processor. And every place that they touch, you get an on and off signal. See that? Those on and off signals is what's going to give you that pulse width modulation. That's your DC pulse. All right? But because it's kind of following along with that AC sine wave, you get what is essentially a pretend AC sine wave. Everybody clear on that? So the faster I make this sawtooth, the more pulses I get per second. The slower I make this sawtooth, the less pulses I get. The more pulses per second, the more voltage I get. The less pulses, the less voltage, because they're not staying on as long. Right? Yesterday I compared it to what? Burping the throttle on your car, right? Or burping the throttle on a motorcycle. Burp, burp, burp. Right?
I think first gear's going out my metro.
If anything, it's the clutch. It's just not like clutch.
It's because he can't drive a clutch.
Better ride it.
Why do you ride the clutch? If it's got synchronous gears in it, which if it's made after 1982, it's got synchronous gears in it, you barely have to use the clutch.
Dude, that car's weird. This clutch is nothing like my Focus.
It's like a dirt bike clutch.
It is a dirt bike clutch because it's a dirt bike motor.
Exactly.
But it's not.
It's a 3-cylinder motorcycle engine in a car.
It's such a Jeep Renegade asset.
Anywho, that's kind of how it's going to work. So that AC sine wave is going to follow along using that sawtooth to produce these little pulses. The pulse width is a direct proportion to how much voltage you're going to get. The skinnier the pulses, the less time we leave those IGBTs on, the less voltage we get. The more time we leave them on, the more voltage we get. Okay? I really don't care if you know this. It has to do with the processor. Don't really care. So what is an IGBT? IGBT stands for insulated gate bipolar transistor. Write that down because that will be on a test probably 2 or 3 times on this test you're going to take. So, those of you that care about passing.
Okay.
Insulated gate bipolar transistor. You ain't gotta write it down.
Attaboy.
I'll remember it.
These are relatively new. Okay? These are relatively new. They didn't come out very, very long ago at all. When they introduced these IGBTs into the variable frequency drives, they cured a lot of the ailments that used to go on along with the drives, okay? But because their switching frequency is so high and they generate so much heat and they generate so much noise, it caused a lot more problems. So they're not the end-all beat-all, but they did replace like just regular transistors or regular, call it SCRs. Like SCRs, you can't switch on and off fast enough to make them fire that fast. So the IGBT fixed that, but the IGBT, because of its nature, caused a lot more problems. They can turn on and off in less than 400 nanoseconds. They can turn on and off literally 500,000 times in a second. But it works just like a normal transistor. So, during the off state, the IGBT gate voltage is held normally at a negative 15 volts. That's to prevent. Anybody ever talk about like negative pressure in a in a vacuum, right? You end up putting negative pressure in it to try to keep dust out, right? It's kind of the same thing. You end up putting negative pressure to make sure that it stays closed. So this thing's not just getting turned on and off, it's actually getting put forward and reverse biased 500,000 times a second, okay? So everybody understands the principles behind the IGBTs, right? Everybody understands the 3 blocks of the diagram for a variable frequency drive, right? We have the inverter, the DC bus, and the converter. The converter is made up of the rectifier, the inverter is made up of the IGBTs. Very important. So this is kind of a cartoony way of looking at it, right? So if I need a 3-phase sine wave, I might turn on switch number 1, and I might turn on 120 degrees later, I might turn on switch number 2. And 120 degrees later, I might turn on switch number 6. And then 120 degrees later, I might turn on switch number 4. Right? Boom, 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 boom. That's going to give me my 3 phases of voltage, or my 3 different voltage sources to give me my 3-phase. Okay? They're just going to keep popping on and off. And they do that. And they do it really fast. Like I said, within nanoseconds. The interesting thing about this, or the thing that I want you to understand about this, is how you would troubleshoot it, right? Because one of the biggest things that companies that come here trying to hire you guys, for whatever damn reason, want you to know is how to troubleshoot the IGBTs on a drive. Okay? That's what they want you to do. So, riddle me this. If you have these IGBTs, where's it at? Oh, I don't have a picture. I'll have a picture here in a second. If you have these IGBTs, I'll draw it. Because I can.
Because you're autistic? I mean, artistic?
Artistic, yeah. Autistic. I'm only going to draw one.
What are you drawing?
You tell me what I'm drawing.
IGBT. That looks like a honeycomb.
Good job. So, on the drive, right, on this variable frequency drive, you have your DC bus. You have access to the DC bus voltage, positive and negative. That's this right here, okay? So, if you have an IGBT, a transistor, okay, and you measure from the positive side of the DC bus to T1, it should act like a transistor or like a diode, like a solid state device. So if you take your voltmeter, your flute meter, and put it on diode checker, if you check from here to here, in one direction, in one biasing or one polarity, you're going to get essentially overload, or you're going to get infinite resistance. Okay? If you flip the polarity, you should get very little resistance, almost zero resistance. If you don't get it, if you don't get what you expect to see, if you don't get infinite and zero, you have a bad transistor. Okay? And you can check both of these IGBTs by going positive to T1 and negative to T1. Both polarities. Alright? And then you do this next same thing to T2, because it's got 2 different IGBTs, a positive one and a negative one. And then you check T3, positive and negative, both polarities. It should go overload on one way, and it should go basically 0.5 ohms, very little resistance, the other direction. If you don't see that, if that's not the reading that you get, the IGBT is bad, which means the drive is bad. Okay? Everybody understand that? Say nothing if I'm right.
You're not right.
Okay.
Don't flatter yourself.
Don't flatter myself. That's a good thing. That's muy importante. Muy importante. That's how you decide if a drive is bad or not. You can also go across the DC bus and check the capacitor. If you put it on capacitance, you can check the capacitor to make sure the capacitor is still working. Because if one of the three things, if the rectifier isn't working, if you go across the DC bus and you check to the L1, L2, L3, you can check if your rectifier is working. If you go across the DC bus and you check T1, T2, and T3, you can see if your IGBTs are working. If you just check across the DC bus with a capacitance, you can see if your capacitor is working. If one of those three things breaks down, the drive is shit. You throw it in the trash, you go get another one.
Whoa, language.
I'm sorry, I apologize. My rule was 100 horse. If anything less than 100 horse, you throw it in the trash, go get another. Anything more than 100 horse, you send it out and have it rebuilt. Because it's not worth you taking it apart and replacing all the crap inside of it. There are companies out there that specialize in that sort of thing, and let them do it. Chances are, if you have a 100 horsepower drive, you can afford to spend a couple grand to have somebody rebuild it. No big deal. Okay? So what is this? This is that volts over hertz frequency, volts over hertz ratio that I was talking about yesterday. The thing about it, like I said, is it has to do with that counter EMF or that reactance that's going on because of the magnetic field or the inductance that's happening inside the motor. Alright? And essentially what you're doing is it's just ratio and proportion. A 460 volt motor running at 60 hertz will have 230 volts at 30 hertz. And anywhere in between that. If you have 416 volts, you can calculate the frequency. Or if you're running it at 45 hertz, you can calculate what the voltage should be coming out of the drive. Don't always expect to see 460 volts coming out of the drive if you're at lower than standard frequency or lower than max frequency. Okay. This has to do with the IGBT principle for the inverter. This just has to do with the time on versus the time off. Again, it's like I said, it's like throttling your car or throttling a motorcycle, right? If I leave that throttle cracked longer, it revs up higher, right? If I just barely crack it, it doesn't rev up as high. That's essentially what this principle is. The longer I leave that IGBT on for, the more voltage I get. The shorter the pulse, the less voltage. Everybody clear? That's on the test. And that's what the math is. Like I said, you can check it. Don't care, don't care, don't care, don't care, don't care. You get don't care, don't care. So there are 4 different ways of controlling it. The majority of them are going to be ran off of what we call the volts over hertz ratio, right? Most of the drives you're going to encounter are going to run off volts over hertz. Okay? You change the frequency, it changes the speed of the motor, and it changes the voltage output of the motor. All right? Hopefully it doesn't affect the torque. So this is actually most of the way. It's relatively cheap. All right? Sensorless vector essentially just tells this thing, a vector drive tells it to turn on and run at a specific speed. So I'm telling this drive that I want to maintain 1800 RPM, or 1900 RPM, or 1100 RPM, right? But it's sensorless. So there's nothing telling the drive that it's at 1800 RPM. It just goes by how much torque or how much force is being applied to the motor. All right? Flux vector provides more precise speed torque control because it has a dynamic response. It actually has some sort of feedback device or some sort of way of monitoring how fast it's going or how much output it's getting. The FOV or the FOC, the field-oriented control, provides the best speed and torque control available for AC motors, and provides DC performance for the AC motor. This provides the best torque control at low speeds, okay, because it applies the principle of a DC motor to an AC motor. You get this field that's being generated, and it's monitoring that field. So they can tell exactly how it's working based on monitoring the magnetic field that's inside of it. It's not monitoring RPM, it's not monitoring amps, it's not monitoring any of that. It's monitoring the actual field that's going on, the actual magnetic flux that's going on inside the motor. Okay? So, all I really want you to know is good, better, bestest, most bestest. Alright? So let's answer some questions, if you guys are interested. True or false?
True.
Very good. What part of the AC drive changes the voltage from AC to DC? The converter changes it from AC into DC. You would also call it a rectifier, but in a drive it's known as the converter assembly, all of the diodes. What is the purpose of an inverter?
Purify the DC.
No.
Change it from DC back to AC.
Changes it from DC back to AC or PWM. That's a synthetic AC. Changes it from DC back to PWM, pulse width modulation. How is the carrier wave used to generate the output PWM signal? The carrier wave is that sawtooth I was talking about. How do we use it? It synchronizes itself with the sine wave. And it goes through an op amp, essentially. And every time they touch, that sawtooth touches that sine wave, it gives me a pulse. So the pulse width is generated by how far apart.
So how do you want us to abbreviate that?
I don't care.
Sawtooth wave.
Sure. What does IGBT stand for?
Integrated gate bipolar.
No. Insulated gate bipolar transistor, not integrated. A 460 volt over hertz PWM AC drive will output what PWM voltage at 47 hertz? 47 divided by 60 times 460. And you get about, about 3, how much?
You said 47 divided by 60? Or
47 divided by 60 times 460. It's ratio and proportion. Google 5th grade math.
60.33.
I can't do that math in my head.
Google 5th grade math.
What compound of a component of a modern AC inverter can be switched thousands of times per second to control the current flow and produce a synthetic AC sine wave for the motor?
IGBT.
IGBT. True or false? An AC drive can be used to provide forward and reverse direction control for an AC motor.
True.
True. It's actually really easy. When a PWM AC drive, what's up?
Shadow text, you know that?
Huh?
Shadow text today?
Oh yeah,
You'll be in shop today?
yeah. I'll be in the shop here in 5 minutes.
Okay, didn't mean no rush. Alright.
Alrighty, thank you. When a PWM AC drive broadens the width of the PWM output, what happens to the motor T-lead voltage? So when that pulse gets wider, or they leave it on longer, what happens to the T-lead voltage? It goes up, or it makes it stronger, or it gets higher, whatever the way you want to put it. Questions? Comments? Describe what the volts over hertz ratio is.
Right, it's fair speed for control and everything.
Yes.
Is what?
Matches
One more time.
matches the frequency to the voltage output so that you don't overcurrent the motor, essentially. It lowers the voltage as you lower the frequency, or raises the voltage as you raise the frequency.
What did you have for 6?
There's a certain point, though. So the thing tops out at max voltage, right? If you go above a certain frequency, right? Let's say you go all the way up to 100 hertz, right? The motor's supposed to be running at 50. So at 50 hertz, you get 208 volts. At 100 hertz, you're not going to get 416 volts, all right? The thing's only capable of putting out 208 volts. That makes sense? The problem, so then it flattens out, it tabletops at the frequency. or at the voltage, but the frequency keeps going up. Okay, so don't expect that frequency or that proportionality to continue past the rated voltage or continue past the output voltage of the drive. It will stop at a certain point, regardless of what you do with the frequency. And then there's a certain point where you get the frequency so low that the voltage is so low that the motor won't operate. Right? If you go down to 1 hertz, one or 2 hertz on the frequency, there's hardly any voltage to actually operate the motor. It can't produce torque. Okay, there's not enough field to do it. Okay, so it will fall on its face down low, and it will hit a tabletop at some point, hit a ceiling on the voltage output. But in between, you got a pretty constant or pretty set ratio that most drives operate at.
What was number 2 again?
7.
Converter. Right?
Converter. That is correct.
And 3 is change it back from AC to DC is purpose of the inverter.
From DC to PWM or synthetic sine wave, yeah.
Oh,
The inverter takes DC voltage and converts it to PWM.
okay.
Are you ranking material?
No.
Not even close.